we can move to the next speaker, Alessia Di Fonso. So Alessia, she's a PhD student at the Information and Communication Technology doctoral program in the University of L'Aquila, and she will talk to us about Moblot, molecular oblivious robots. So please, Alessia.
Good afternoon. Today I'll be presenting a Moblot molecular oblivious robots in a joint work with Serafino, Cicerone, Gabriele Di Stefano, and Alfredo Navarra from the University of L'Aquila and the University of Perugia. Swarm robotics emerged from the biological class of self-organized systems like colony of bees or ants. These swarms are made of similar entities in which each individual has limited abilities compared to the complex behavior shown by the whole system. Like in a swarm, robots are modeled as having little skills and must cooperate with others to reach a common goal. And organization emerged from the interaction between the robots and the environment. A swarm of robots is potentially more robust and flexible than a single robot. And it's an ongoing research in engineering and in control theory. But the coordination of a multi-robot systems are challenging also at an algorithmic level. In fact, the goal of theoretical swarm robotics is still to determine if a certain task is achievable by a group of robots and under what assumptions, and also to develop efficient algorithms. Here's an outline of the presentation. First, we talk about a model for the so-called robot computing and introduce Moblot, a novel model in the context of theoretical swarm robotics, and show how molecular robots can be combined to create bigger robots, complex structures, in fact, in the formulation of the matter formation problem. Then we show the symmetry breaking abilities of molecular robots and show a simulation of the algorithm in the presented case study. Robots are modeled according to the Moblot model, one of the well-studied model in theoretical swarm robotics. Robots are modeled as being weak entities, and the reason to use this model is to make it general and robust enough to be able to describe a wide range of scenarios. Robots are modeled as points able to move in some environment, for example, the Euclidean plane, and so therefore they are dimensionless. They are also anonymous, they don't have any ID. And since many robots are involved, a centralized control wouldn't be efficient or scalable. Therefore, robots must be autonomous. They all run the same deterministic algorithm. And they are oblivious. They have no memory of past events. They are also silent because they have no means of direct communication. And each robot refers to a local coordinate system that might be different from robot to robot. And they have sensory abilities allowing to determine the position of all the other robots relative to their own location. The communication between robots is indirect. Each robot interacts with the environment, acquires information from the environment, and this information is the position of all the other robots. The behavior of a robot can be described according to the sequence of 4 states: wait, look, compute, and move. In the look phase, the robot observes the environment and gets a snapshot of the position of all the other robots relative to their own position. In the compute phase, the robot performs a local computation according to a deterministic algorithm, and the result of this computation is a destination point along with a path to reach it. In the move phase, the robot goes to the computed path. When a robot is in wait, we say it is inactive, otherwise it is active. When a cycle ends, a robot can either sleep or start a new cycle. Robots are memoryless. And when a cycle ends, they forget everything. And when they wake up again, it's like the first time. A robot can rely only on the look phase to understand the state of advancement of an algorithm. These are the fundamental features of the Moblot model, while specific instances are defined by the duration of the robot cycle and by the time at which they are activated. In the full asynchronous scheduler, robots are always active, and the duration of a robot cycle can be divided into global rounds. Each robot starts simultaneously the cycle and executes it synchronously. At the opposite, in the asynchronous model, robots do not share any common notion of time, and each robot is activated independently from others, and a robot cycle can have a finite but unpredictable duration. And the choice of the model impacts on the challenge of the problem. It's more difficult to coordinate the robots to reach a common goal. Moreover, in the asynchronous model, robots can be seen while moving, and the computation can be made based on obsolete information about position. One of the most studied problems is the pattern formation problem, in which robots are guided to form a shape given an input to the robots as a set of points in an ideal coordinate system. Due to the lack of a global coordinate system, the pattern is formed when the configuration becomes similar to the one given an input with respect to translations, rotations, or reflections. Today, we present Moblot, a new model in the context of theoretical swarm robotics, in which robots are combined to make bigger robots. The inspiration comes from nature, in which atoms combine to make molecules, and molecules acquire new properties compared to single atoms. In Moblot, robots are modeled according to Moblot, plus they can be of different kinds, property modeled with being of different colors. And they also endowed with chirality, that is, robots share a common clockwise orientation. The algorithmic goal for robots is to form molecules. A molecule is specified by a pattern. Once the robots come close and they are correctly positioned according to the pattern, they bond to form a molecular robot. Once bound, the robots inside the molecule move synchronously together. And the molecule occupies a space, and we consider this disk the space occupied by the molecule, and the molecule can also be oriented. Once formed, a molecule is a new computational entity that can move and accomplish new tasks. One of them can be pattern formation, but in general, it can be any task. In some cases in nature, molecules can further bond to form more complex structure. And in the matter formation problem, we guide these molecules to form a second order pattern that we call the matter. Matter is given an input to the robots in a very general way according to some adjacency properties, so it can scale at any dimension. While molecules cannot be broken back into robots, the matter can be reconfigured to get the different shapes. Whether a matter is achievable or not, that depends on the symmetry of the configuration of robots. We'll show that molecules are able to get shapes that are impossible to have with just robots. In fact, we'll show that molecules are able to break certain symmetries. Each robot runs the same algorithm, and the compute phase depends on the look phase. If two robots have the same view, then they are symmetrical. These robots are called equivalent. Having the same view, they will compute eventually, in the worst case, the same move. If, for example, one moves to the right, its equivalent will do the same. When we move these robots to form a pattern, equivalent robots will eventually move together, keeping this symmetry forever. And this limits the pattern that can be achieved in output. Informally, the symmetricity of a configuration is the number of equivalent robots. More formally, given a set of points and a partition of them in regular polygons of m size, The symmetricity of the configuration is the maximum value of M, such that there is a regular partition of the configuration into polygons of M sides. In this case, the symmetricity is 2. In Moblot model, only patterns with the same symmetricity of the configuration or a multiple of the current are achievable. Symmetry is a measure of the stiffness of the system. The greater the symmetry, more robots will move together in the worst case. Things behave differently in Moblot, in which equivalent robots can be guided to the center to form a molecular robot. In this case, the molecular robot will have the same symmetricity of the system. When we move this molecule from the center, the whole configuration becomes asymmetric. And for an asymmetric configuration, any pattern can be achieved in output. Therefore, now robots are identifiable and can move individually. We now present an algorithm to solve a particular case of matter formation in which we want to enlight the symmetry breaking abilities of the molecules. In fact, starting from a configuration with the symmetricity 2, we show that molecules can form a matter with a final symmetricity of 3. That is impossible in Moblot with just robots, since 2 and 3 are prime numbers. The matter formation problem is break down into sub-problems easy enough to be tackled by a group of robots. Each sub-problem is a task, and each task has an associated precondition and a move. A precondition must be fulfilled in order to perform the task. And the precondition is a predicate that captures topological features of a configuration of robots. During the compute phase, the robot finds that the precondition is true, then performs the associated task. This approach requires that predicates must guarantee some properties. Each predicate must be computable in any look phase, and the predicates are disjoint, and given the pattern for every perceived configuration, there must be a predicate evaluated true. If all these properties hold, the robot recognizes that the precondition is true and performs the move associated. Here we see the transition between system states. The robot recognizes in the look phase the state of the system and move accordingly. The movements of the robots bring the system to the next state. Here we see a simulation of the algorithm. The robots evaluates all the preconditions from the bottom up until they find one that is true. The design of the preconditions is hard because preconditions must be valid during the movements of the robots and until the task is completed. Now we're seeing the robots will start to move from the center in order to make space for the matter. Suppose the robot falls asleep while performing its move. When it wakes up again, it evaluates again all the predicates, and if it has the same output, it will perform the same move. Each robot runs this algorithm independently and asynchronously. Now we see the advancement of the algorithm. Now robots are moving on a circle, and then we'll see that in the following states, molecules will start to form on the circle. Then the molecule in the center is moved so to break the symmetry of the configuration. And the formed molecule on the circle moves toward the final target following a spiral. Then more molecules are formed on the circle and move toward their target until they are all correctly positioned according to the matter. When the matter is formed and all robots are correctly positioned, The robots recognize that the matter is formed and no more moves are required. And here we see that in task T9, the system is in its final stage and no more moves are required. We introduced Moblot, a novel model in the field of theoretical swarm robotics. We have shown that molecules are made bonding robots together according to a pattern, and they can be considered like building blocks to create further patterns, the matter, using a hierarchical approach to the solution of the pattern formation problem. We have seen that molecules are able to enlarge the class of achievable patterns, breaking the symmetry of the system. Further research will be about the design of a general algorithm for the solution of the matter formation problem and to study its reconfigurability. Thanks for your attention.
Thank you, Alessia. I see a question, yeah. So I understand that this robot is conceptual, but what are the challenges for its physical realization? And what sensors and actuator would it require, soft or hard material?
Okay, so these are models for swarm robotics and to reason about the coordination of multi-robotic systems. An application in the short term might be to model the coordination and the configuration of swarms of drones, for example. And this approach may give hints to use the swarm of robots also in groups. We have a big swarm of robots that can be partitioned into groups, and each group can perform a task, can collaborate to hierarchical solve a general task, but also each group might solve a task on their own. So we are looking forward to test this algorithm on the prototyping platforms in the near future.
Thank you, Alessia.